All right, so chapter 5, rational root and power functions. We are now going to look at 5.2, which is looking deeper into rational functions and their graphs. So rational functions have asymptotes. An asymptote is a line that you approach but never cross. So vertical asymptotes are always going to have an equation of x equals. It comes from having 0 on the bottom of an equation. So in a graph, a vertical asymptote is going to be a line like this that the graph gets closer and closer to, but never touches or crosses. Horizontal asymptotes are y equals. They're the same idea, but a horizontal line. The biggest difference, other than the horizontal and vertical aspect, is the horizontal asymptote can be crossed by one piece of the graph while other pieces approach it. You can have as many vertical asymptotes as there are in the equation, but horizontal, you can only have one. To find a vertical asymptote, you set the denominator equal to 0. So for f of x, we would say x plus 1 equals 0. Subtract 1 from both sides, and our vertical asymptote would be x equals negative 1. G of x, we would do the same thing, but because we have a quadratic, we need to factor it. So 2, 5, and negative 6. Negative 1 times 6. Greatest common factor. Multiply up, multiply across. We get x plus 3 and 2x minus 1. And now we solve each of those. So if x plus 3 equals 0, we subtract 3. So one of our asymptotes is negative 3, while the other, add 1 to both sides, divide by 2. The other one is going to be x equals 1/2. So again, to find the vertical asymptote, you set your denominator equal to 0. There are 3 rules to find your other asymptote that make your life easier. If the numerator degree is less than the denominator degree, it will always, always, always be y equals 0. If the numerator degree equals the denominator degree, your horizontal asymptote is going to be y equals a to the n over b to the n. You just divide those leading coefficients. So whatever coefficient goes with the term with the highest degree, divide those and you get your horizontal asymptote. If the numerator degree is 1 higher than the denominator degree, you could have an oblique asymptote, which is going to be a diagonal. So you do the division and then use your quotient without the remainder to be your asymptote. So let's look at a few of these. Okay, so this first one, vertical asymptote. We set the bottom equal to 0. Subtract 1 from both sides. Square root of negative 1 is I. And since that's not real, there's no vertical asymptote on the graph. Because that's not real. Horizontal, on the top, our degree is 0. On the bottom, our degree is 2. 0 is less than 2, so our horizontal asymptote would be y equals 0 by that first rule. Let's do another one. Find the domain and asymptote. So our vertical asymptote, set the bottom equal to 0. Add 3. Vertical asymptote is x equals 3. That asymptote helps us with our domain. Polynomials are negative infinity to infinity. And then your vertical asymptote is where that domain breaks. So you just do negative infinity to infinity, but you put a break at the x equals 3. Now look at our horizontal ones. The degree of the top is 1. The degree of the bottom is 1. So we're going to divide the terms in front of that x. So this one's a 2. This is a 1. So our horizontal asymptote is 2 over 1, or 2. vertical asymptote. We're going to tic-tac-toe. So 3, 5, -6. We would get -1 and 6. 3, 1, -1, 2. So x plus 2, 3x minus 1. So this vertical asymptote is going to be x equals -2. And this vertical asymptote is going to be x equals 1/3. So our domain is going to be -infinity to -2. Then we go from -2 to 1/3. Then we go from 1/3 to infinity. Degree on the top is 1. Degree on the bottom is 2. 1 is less than 2. So our horizontal asymptote is going to be 0. All right, let's try this one. Vertical asymptote. Set the bottom equal to 0. Our vertical asymptote is going to be x equals 2. So our domain is going to be -infinity to 2 and 2 to infinity. Now our other one, 2 is higher than 1, so we actually have to do the division out. So if you remember from chapter 4 and our synthetic division, inside we would have 1, 0, 1. Outside, we take the opposite, so it'd be +2. Bring down the 1. Multiply. Add. Multiply. Add. And we ignore the remainder. So our oblique asymptote is going to be y equals 1x plus 2. So you just do the division and then ignore the remainder and you get your oblique asymptote. If we were to graph this, we graph the asymptotes. And then once we test some areas, we're able to figure out where the curve goes. The calculator will also do that for you. A comprehensive graph. So we're adding asymptotes now. You need all the x and y intercepts. You need all the asymptotes. You need a point where if it does cross the non-vertical one, you need that point, and you need to be able to show the end behavior. So we're getting more specific about our graphs. These are the steps to do a graph. Find the domain in your vertical asymptotes. Find non-vertical asymptotes. Find y-intercept, x-intercept. See if there's any intersection, and then use those points to make intervals and graph from there. So if this is our equation, 2x plus 1, and then the bottom was 3x squared plus 14x minus 5. All right, just making sure the camera's still on. Yep. All right, so step 1, vertical asymptote. Set the bottom equal to 0. And tic-tac-toe. So we get 15 and -1, 3, 1, -1, 5. X plus 5, 3x minus 1. So our vertical asymptotes are going to be x equals -5 and x equals 1/3. Use those to make our domain. -infinity to -5, -5 to 1/3, and 1/3 to infinity. Remember, domain always goes least to greatest. Let's look for our others. Degree of the top is 1. Degree of the bottom is 2. 1 is less than 2. So we have a horizontal asymptote of y equals 0. Now we're going to look for our y-intercept. Well, y-intercepts are when x equals 0. So to find the y-intercept, we just plug 0 in for x. And we end up with -1/5 as our y-intercept. So I'll put that over here. So it'd be 0, -1/5. X-intercepts are when the equation equals 0. So we plug 0 in for the f of x. If we multiply both sides by that denominator, Well, 0 times anything is 0. So your x-intercepts, really, you make your numerator equal 0. So to solve for x-intercepts, make the numerator equal 0. And then subtract 1 from both sides. Divide by 2. X equals negative 1/2. So that's our x-intercept. And then we test for intersection with our horizontal. So we would plug in this equation for y equals, which is what we did right here, and solve for x. So multiply both sides by 0, and it's going to intersect the horizontal asymptote at negative 1/2. So now we use our domain and our intersection point to make intervals to test. So we go from negative infinity to negative 5. Then negative 5 to negative 1/2, because that intersection point is going to change things. Negative 1/2 to 1/3 to finish that bracket. And then we have the last interval, 1/3 to infinity. So we're going to pick a number in each of those. So if this was negative 6, let's say we chose negative 1, let's say we chose 0, and let's say we chose positive 1. We're going to plug that in and look for two things. We're going to look if it's above or below the x-axis, and we're going to look if it's above or below the horizontal asymptote. Most of the time, those will be the same, but once in a while they won't, so you just want to be careful. So if I put the equation, if you put that equation into L1, so our y, so if I do parentheses, 2x plus 1 divided by, what was the bottom? 3x squared plus 14x minus 5. Now we have that in there. In our calculator, we can store any number we want as for x. So if we say negative 6 and choose this store button for x, now whenever we plug in negative 6, or x, it'll plug in negative 6. So if I go to vars, function, and choose y1 and hit enter, that's the answer when I get negative 6 in there for x. So 3x squared plus 14x minus 5. Well, that's different than what I got. 2x plus 1, 3x squared plus 14x minus 5. Negative 6 stores x, y1. Let me just make sure I'm typing these things right. 2x plus 1, 3x squared plus 14x minus 5. 2x plus 1. Interesting. All right. And then 2x plus 1 divided by 3x squared plus 14x minus 5. Oh, I forgot the x up here. See, I do that all the time. I forget things. Okay. Now it should work. So we get negative 0.58. So in our chart, it's below the x-axis and below our horizontal asymptote. Then I'm just going to repeat that with each x value. So if I store negative 1 in for x, I get 0.06, which is positive. If I put 0 in for x, I get negative 0.2, so that's negative. And if I put 1 in for x, I get positive 0.25. So now we know in each of those intervals whether we're going to be positive or negative. So let's set up a graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we want to put our vertical asymptotes at -5 and 1/3. So -5 is here. And 1/3 is about here. And our horizontal asymptote was y = 0. So now those are graphed. Now we want our intercepts. So our y-intercept was -1/5, and our x-intercept was -1/2. And now we do our intervals. So the first interval was this area right here, -∞ to -5, and we said that was negative. So we're going to be below the asymptote in the axis. Our next interval was -5 to -1/2. And then we had -1/2 to 1/3. So before this intersection point, we're positive. After this intersection point, we're negative. And we want to make sure we go through our intercepts. And then our last one was 1/3 to infinity, where we were positive. So those pieces don't have to be exact. You're just using that information that you came up with to sketch each section. So we just did that. All right, so you try this one. Find those 7 steps and then do the graph and then come back and check. Okay, vertical asymptote, denominator equals 0. So if x² equals 1, our asymptotes are going to be +1 and -1, which makes our domain -∞ to -1, -1 to 1, and 1 to infinity. Degree is 2 on the top and the bottom, so we use the leading coefficients to get our horizontal asymptote, which is 2/1, or 2. Y-intercept, we plug 0 in for x. Well, if you have 0 on the top of a fraction, it equals 0. So our y-intercept is 0, 0. X-intercept, set the numerator, equal to 0 and solve. So if we divide by 2, square root of 0 is 0. So our x-intercept is also 0, 0. We test for intersection points with our horizontal asymptote by setting the original equation equal. So since it's 2 this time, we're going to say 2 equals our equation. Multiply both sides by that denominator. We're going to distribute, so 2x² minus 2 equals 2x². Subtract 2x² from both sides, and we get -2 equals 0. That's not true, so that means there's no intersection with the horizontal asymptote, because that's never true. Now we're going to test our intervals. So it's just our domain since there's no intersection point. So we have -∞ to -1, -1 to 1, and 1 to infinity. So we could test -2, 0, and 2. So let's see. If I plug -2 into our original equation, 2x², x² minus 1. So again, you can do it by hand. You can put it in your calculator. It's completely up to you how you want to plug these in. But if you plug in -2, you get 2.66. So we've got our x-axis and our horizontal asymptote. It's above both of those. If I plug 0 in for x, I get 0, which is on the x-axis and below the asymptote. Then if I plug 2 in, I get 2.66, which is above it. So if I'm graphing, I'm going to put my vertical asymptotes. And then the horizontal one was y equals 2. So I'm going to put a line there. And my x and y intercept was 0, 0. Now I use these. So the first section, we're above both things. The second section, the highest point is going to equal 0. If we're not sure whether it goes above or below, we can always test each 1/2 if we wanted. But it's going to look like this. And then the last piece is above. So there's that graph. All right. So let's try another one. Vertical asymptote. When the denominator equals 0. So these are both x plus 4, which means our vertical asymptote is going to be x equals -4, which makes our domain -infinity to -4 and -4 to infinity. Horizontal asymptote, the degree on the top is 2, the degree on the bottom is 2, so our horizontal asymptote is y equals 0. Y-intercepts, we plug in 0 for x. So 3 times 0 squared is 0, minus 3 over 6, same thing on the bottom. All of this is going to cancel out because of the 0, so we get -6 over 16, which reduces to -3 over 8. So our y-intercept is -3/8. X-intercept, we make the top equal 0. So we tic-tac-toe. Well, I'm going to actually take out the greatest common factor first. So 3x squared divided by 3 is 1. 3 divided by 3 is 1. 6 divided by 3 is 2. Now I have smaller numbers up here to deal with. So -2 and 1. So we get x plus 1 and x minus 2, which means our x-intercepts are going to be -1 and +2. Test for intersection points with y equals 0. Well, we could plug 0 in, but we know it's the same thing as the x-intercept because of where the horizontal asymptote is. So we know those x-intercepts are also going to break up our domain. So we figure out our intervals. We're going to go -infinity to -4. And then -4 to -1. -1 to 2. And 2 to infinity. So we have the same two pieces from our domain with these intercepts broken in. 3x squared minus 3x minus 6. And then the bottom is x squared plus 8x plus 16. Okay, so we're going to plug in a number from each interval. -5, -2, 0, 3. So if I plug those in, (3x squared minus 3x minus 6), x squared plus 8x plus 16, -5 in for x, we get 84. So it's above the x-axis, above the horizontal asymptote. Plug -2 in, we get 3. So that's above the x-axis, above the asymptote. Did I do that right? -1 and 2, yep. Okay. 0. We get -0.375. And then 3, we get positive 0.24. So I just want to check that again. 3x squared minus 3x. Okay. So if I draw my graph, we're going to plot the asymptote, which was -4. And the horizontal one, they were equal, so it shouldn't have been 0. I messed up here. It should be 3 over 1. So y equals 3. Which means I need to test the intersection point of 3. So if I test that, y equals 3, is that what I said? I'm going to plug 3 into the equation for the equal sign. Multiply both sides by the denominator. Distribute. And then subtract combine like terms. So the 3x squared will delete itself from each side. Add 3x. So we get 27x plus 48 equals -6. Then subtract 48. 27x equals -54. Divide by -54. X equals -2. So if x equals -2, I need to test another point in here. So I'm actually going to break this into -4 to -2 and -2 to -1. So we can test -3 and -1.5. So this is positive and positive because I got 30. And then if I test -1.5 in there, I get 0.84, which is above the x-axis, but below our horizontal asymptote. So go back to where we were doing that. So I skipped one of the steps here. So there are our asymptotes. We know that x-intercepts are -1 and 2. We know the y-intercept is -3/8. And we know that we intersect the asymptote at x equals -2. Now we can plot. So in our first section, -infinity to -4, we're above. In our second section, -3 to -1.5, we're above. Our third section is this little piece, -2 to -1. We're above the x-axis, but below the asymptote. Then from -1 to -2, or to 2, we're below, but we also have those points, so we have to touch those points. And then that last one was a 0.84, so that's above 0, but below the axis, so we're kind of going like that. You can always check your graph by putting it in the graphing calculator and seeing if what you drew is about the same. And if not, you might skip a set. You might do what I did and say, "Hey, I skipped a step. Wait, I did the horizontal asymptote wrong." So that's that graph there. All right, let's see. Graphing a rational function with an oblique asymptote. So vertical asymptote, we test the bottom, we get x equals 2. Our domain is -infinity to 2, 2 to infinity. We divide these. So 1, 0, 1 inside, +2 outside. Bring down, multiply, add. Multiply, add. Our oblique asymptote is going to be y equals x plus 2. Y-intercepts, we plug 0 in for x, and we would get negative 1/2. X-intercepts, we set the top equal to 0. X squared equals negative 1, so we get x equals plus or minus I, which means on a graph, there's no x-intercepts. And then intersection point. So we want to test if this ever crosses that. So we say x plus 2 equals x squared plus 1. Multiply both sides by the denominator. So we're going to distribute this. It's difference of squares. So we get x squared minus 4 equals x squared plus 1. If we subtracted x squared from both sides, we'd get negative 4 equals 1. That's never true, so it doesn't cross the oblique asymptote. So we just have those two pieces of our domain to check. So we have negative infinity to 2, and we have 2 to infinity. And our graph was x squared plus 1 over x minus 2. So I'm going to check 0, and I'm going to check 3. Divided by, all right, 0 stores x. So this is negative 0.5. So we know it's above the x-axis, and then if we store 3 in there, we got 10. So graph our equation. Our horizontal intercepts was, our vertical one was 2. And then the oblique asymptote was x plus 2. So we know the y-intercept is 2. Then we go up 1 over 1, up 1 over 1, up 1 over 1. So our oblique asymptote looks like this. We said the y-intercept was negative 1/2. There were no x-intercepts. When x equals 0, we're below the graph, which we know. And when x equals 3, we're above. So our graph's going to look like this. We just need our two pieces that fit into there. And then this shows it graphically. Okay, hole in the graph. This is the last thing we're going to do on this section. Make sure that before you start doing your dividing and such, that everything's in lowest terms. This numerator is a difference of squares that breaks up into x minus 2, x plus 2. So this blue is the same as this black. Well, we have x minus 2 on the top and the bottom, so those cancel, making a hole where that equals 0. So it makes a hole because it cancels out and it's not really part of the graph, so we don't have to worry about an asymptote. Then all we're left with is f of x equals x plus 2 once it reduces. So we don't have to go through all of that information because we know how to graph x plus 2. Y-intercept is 2, and then we go up 1 over 1, up 1 over 1, up 1 over 1, and so on and so forth. So we draw our line. The only difference is when x equals 2, we have a hole in the graph instead of a point. Now, if after we had reduced, we had had other numbers that didn't cancel out completely, we would have still had to go through everything. So if your window's right on the graphing calculator, it'll even show the hole, which is kind of exciting. So let's do this one. The top factors out to x plus 1, x minus 1. The bottom factors out to x minus 2, x plus 1. So the x plus 1's cancel. We know we have a hole at x equals negative 1. We still have a denominator, so we're also going to have a vertical asymptote at x equals 2. the degrees are the same. We have a 2 and a 2. When they're the same, we just divide the coefficients. So our horizontal asymptote is going to be y equals 1. Now we can use our reduced fraction to do the rest of this. So let's use that. So our y-intercept is when it equals 0. So we'd get -1 over -2, which is positive 1/2. X-intercepts are when the numerator equals 0. So x minus 1 equals 0. Our x-intercept would be 1. Test for intersection. We're going to make this whole thing equal 1. Oops, what am I doing? 1 equals x minus 1 over x minus 2. Multiply both sides by x minus 2. Subtract x from both sides. -2 never equals -1. So we have no horizontal asymptote intersection. So now we're going to test our domain, which I forgot to write with the range, with the hole here. So we go -∞ to -1. We treat the hole just like a vertical axis with our vertical asymptote with our domain. So -1 to 2, and then 2 to infinity. Because we have no intersection, we don't need another break there. So I'm going to test -2, 0, and 3. Oh, I better hurry. All right, so if I put either equation in, sorry, it keeps spinning, it should work, but I'm going to test with the original just to make sure. X squared minus x minus 2. So if I plug in -2, I get 0.75. So it's above the x-axis, but below the horizontal asymptote. If I plug in 0, I get 0.5, which is above the x-axis, below the asymptote. And if I plug in 3, I get 2, which is above the x-axis and above the asymptote. So if I graph this, I have a horizontal or vertical asymptote at x equals 2, horizontal asymptote at y equals 1, y-intercept at 1/2, x-intercept is 1. And then we follow. So we're above but below the asymptote. So we're going to go like this. And then the top piece is above, so it's going to go like this. So now you have that last graph. And I think that's it. There can be no vertical asymptote. So if you look at this one, x squared plus 1, that never, if you equals 0, x squared -1, square root is I. So there's just no vertical asymptote. So if you were to put that one in the graph, it would look like this, and it would actually touch that point. So that is 5.2. Let me know if you have questions.